Okay, as I was saying, we'll start looking at the kinetic term. When we are using generalized coordinates, we'll see what are the differences compared to using Cartesian coordinates. Okay. Okay. So, first, what do we see when we work with Cartesian coordinates? It will be nice to have color. Let's see if I can do it quickly. I can. Good. I think it is done. Cartesian. Okay. So what do you see when you are using Cartesian coordinates? You get t as half mi. Let me put r dot. Okay, half my ri dot square. That's what it is. Okay. So this is of course quadratic in velocities. Note that there is no term which involves the product of velocity of particle I with the particle j. Okay, there is no such term. So they are all t is really diagonal in the velocities. Okay. Also note that there is no factor in here which depends on the coordinate itself. So t does not depend on the coordinate but only on the velocities. There's another thing. And also note that there is no linear term. It's all just quadratic. Okay. So when you are using generalized coordinates, t is quadratic in r dots. Okay. Note that there is no dependence on r. Okay. And also, for example, there could have been a r square dependence, okay, which is absent. And also there is no what I wanted to say, there is no ri dot rj dot kind of a term here, okay, where I is not equal to j. You have only the terms where I and j are equal, right? So there are no cross terms. TERM. No cross terms are present. And let's see what the situation is when we start using generalized coordinates. Oops. Okay. Let's see if I can make okay. I don't know why I'm making it colorful, but let's see. Okay, good. Now I don't know how to go get the green back. Oh, that's sad. Yeah, here is the green. Okay, let's look at the generalized coordinates now. Yeah, we have already looked at t in at least few contexts, and you remember when we were looking at a particle which was moving in 2 dimensions, xy plane, and we were using polar coordinates. At that time we wrote the kinetic energy of that particle in polar coordinates, and it was half m r square theta dot square plus r dot square. So in this example itself, you see that this condition is this thing is not true, right? Generalized coordinate r can appear, or in principle in some different context some other coordinates could also appear. Okay, so it's not just the generalized velocities theta dot and r dot appear, but also coordinate itself can appear, which is the case here. Here it is still of the form where cross terms are not present, so you still don't have a term like theta dot r dot. But as I will show that this is also not a general statement. In principle, they can be present. Okay, that's one thing. And also here you don't have a term which is just involving the velocity of one of the coordinates, and as you're going to see very soon, that is also not a general statement. So let's see what the general expression would be. This was one specific example, okay, which we covered in one of the previous videos. So in general, the kinetic energy can be written as a sum of three terms, okay, which I will call as T0 plus T1 plus T2, where T0 is independent of q dots. Okay, independent of the generalized velocity. So let me put alpha, and alpha will run from 1 to whatever degrees of freedom you have. So it will be independent of all the generalized velocities, and that is what 0 signifies. T1 is a term which will be linear in generalized velocities. Linear in generalized velocities. Which is q alpha dots. Okay, then T2 will be quadratic in q dots. Okay, that's what we'll prove now. Okay, so what I want to prove is this, that let's see, yeah. So I will introduce a notation and make what I said just now more explicit, that T will have the form T0 plus, I said that this will be, T1 would be linear in velocities, so T1 would be having a form like q alpha dot times some coefficients or some functions. Let me call it T1 alpha. Okay, I distinguish this T1 alpha from T1 because T1 has no index and this guy has. So it's not the same quantity. So you have T1 alpha and there'll be a sum over all the alpha. That's good. Then as I said, there'll be terms which are quadratic. So you could have q alpha dot, q beta dot, and T2 alpha beta summation over all alpha and beta. Okay, so whatever I said here is more explicitly written here. And note that I am saying that it's not q alpha dot q alpha dot. I'm saying q alpha dot q beta dot because cross terms may be present. Okay, and this is what we want to prove now. And proof is simple. Proof. Okay. So what do I have to do? Just remember that half mi ri dot square sum over all the particles. Good. Now your Ri will be related to your generalized coordinates by the following: Ri q1 to whatever q you have, let's say 3n minus k, total number of degrees of freedom, and it could also possibly depend on time. Okay, your constraints on the system may be changing with time, so your transformation from R to the generalized coordinates would involve time as well. That's good. All I have to do is take the time derivative so that I get an R dot, and take the R dot square and put in here. Okay, that's all I have to do, which is not difficult. So dr, just a second, hold on please. Okay, so the velocity is dr I over dt, which is del ri over del t. So you take the partial derivative, and then you take the partial derivative with respect to all the coordinates alpha, ri, and you have q alpha dot, and you should sum over all the alphas. That's good. Now I take this, which is ri dot, and square it. Ri dot square. Okay, so I write this as del ri over del t plus the same thing which you have above. Okay, then I should dot it with again the same piece, delta ri, remember I is the label for the particle, delta t plus summation delta ri over delta q alpha dot summation over alpha. Okay, now if you have not already noticed the mistake, and if you have not noticed still, despite my telling that it's a mistake, you need to know one thing, that this is going to give a trouble if I use the same index alpha which is here and the same index alpha here. Okay, I should be very careful, and I should not use the same index on both the sides. So it will be wiser to change alpha to beta. Okay, q beta, q dot beta. Okay, and I leave it to you to figure out what will be the problem if I use alpha in this piece and alpha in here also. Okay, you should know why you'll get in trouble. Okay, that's good. Now I should take the dot products. What happened? Yeah. Now this, so I take a dot of this with that, which is easy. R over delta t square. Okay, then I will take a dot product of this piece with this term. Okay, del r, this piece with that term, and you will have another similar term coming from this one and this one. Okay, they are both same because the alpha is dummy. Okay, I'm just summing over all possible alpha. So in these two products, this times that and this times this, I can use the same indices. Okay, maybe I'll go slowly so that you can see. Plus, let's multiply this with that one. So I get delta ri over delta t, that is correct, dot summation over beta delta ri over delta q beta dot, and then you look at the product of this guy with this guy, which is delta ri over delta t coming from here, dot summation over alpha delta Ri delta Q alpha dot. Okay, this dot product is because of the two vectors here. That's good. And then you have one more term plus product of these two. These two will give you term which is quadratic in the velocities. Okay, these ones are generating terms which are linear in velocity. There is only one velocity involved here, plus, so I write down summation over alpha summation over beta delta Ri over delta Q alpha dot, because there is a dot product here, delta Ri delta Q beta, and then you have Q alpha dot Q beta dot, Q alpha dot Q beta dot. Now what I was saying earlier was that this beta here can be replaced by alpha. It doesn't matter, right? You're just summing over all the coordinates and multiplying with the relative corresponding velocities. So I will replace this beta by alpha. Then these two become identical and the sum will have a factor of 2, which is so these two together become 2 delta Ri over delta T dot summation over alpha delta Ri over delta Q alpha dot. Okay, that's good. So this is what I was claiming here. First term, no velocities are involved in here, but this is a function of Q and T. Okay, right now I'm writing R as a function of Q and T, right? So this is a function of Q and T, but there are no velocities involved in here. So that belongs to T naught. Then this piece has only linear dependence on the generalized velocities. So that's what is here. And so you can read off from here after summing over all the masses, okay, and all the particles, your T1 alpha. And this is the one which is going to give contribution to T2 alpha. Okay. So let's see, I will write this down, what happened. Okay. So here we have, or maybe I can, let's see if I can do it there itself. Let's, okay. Yeah, maybe not. Let's be neat and clean. So I will write T as, I'm just now bringing in the half mi, which was remaining, and I have to sum over all the particles. So if you look at what we had earlier, I had dt square, right? Let's see, Ri del over del t of the square. So that's the first term, which is what your T0 is now. Let's look at the second term. Good. I will multiply this with half mi and sum over all the i's. So you'll get summation over I 2 times half of mi delta Ri over delta T dot delta Ri over delta Q alpha. Okay, and this is the summation over alpha, which I can take out, and I can put the summation over I in here and put the summation over alpha here. This entire thing with Q alpha dot. So let's check. Q alpha dot, this summation I have pulled out and the sigma over I have pulled in. So this is the piece, which is this piece. This entire thing is your T1 alpha. Good. Plus the term which is quadratic in velocities, and here you will have summation over alpha and beta, then summation over I, half mi, and we had delta Ri over delta Q alpha, Q beta. Very good. Q alpha dot Q beta dot, and this is what your this piece is, T2 alpha beta. Let's see, what did we call T2 alpha beta? Yes. Okay, so I have proved what I was claiming, that you have all kinds of terms here, and note that these coefficients T1 alpha and T2 alpha beta and T naught, they depend on generalized coordinates and time in general, and there may be cases, depending on what kind of coordinates you are using, that some of the coordinates may not appear, and some of velocities generalized velocities may not appear linearly, but those will be specific to those cases. But that's the general result in front of you. Okay, we'll stop this video here and we'll meet next time.